primary operators and their descendants. Okay. And I showed you last time how the primary operators transform, namely like tensor densities. And I want to show you today how their descendants transform. And the point that I want to make here is that if we know how primaries transform, then we can derive how their densities, how their descendants transform. Okay, literally, we just take derivatives. So that's what I want to do today. And then I'll, by way of an example, just elaborate a little bit on this point that I was making, that unitarity actually gives us some strong constraints on the theory. In fact, we showed that unitarity, requiring that the theory be unitary, bounded the conformal dimension of operators, right? And unitarity is tied in a rather intimate way to the norm of operators, right? And I want to elaborate a little bit on that and show you how, why, when people talk about unitary theories, they're talking about the norms of the operators in the theory. And then finally, I'm going to show you that, again, tied to this idea of norms and unitarity, the theory fails to be unitary if you find negative norm states. So you calculate the norm of a state, the length of a vector in the vector space, and it comes out to be negative, then you know that I'll show you how that means that the theory fails to be unitary. And there's a marginal case where the theory is just becoming non-unitary. We will start to find null states in the theory. Null states are theories that have null states are states in the vector space that have zero norm. So we start to find states in the theory that have zero norm, right? And this will give us the bounds on the theory. So I'll do an example where we'll illustrate this very specifically. Okay. So we worked out last time the transformation properties of primary operators. Let's see how descendants transform. So the question today is, how do descendants transform? So just by way of recollection, given some primary field phi, the descendant operator associated to this field is the field that I get by acting on phi with p mu. P mu acts as a raising operator for the conformal dimension, right? P mu was I d mu, partial d mu. So acting on the field with P mu is the same as taking its derivative. So descendant operators are that are associated to the primary phi just look like the derivative of phi. Okay, so that's what I mean by descendant operators. So the question is, how do these things transform? And to be concrete, let's focus our attention on just the first descendant, or level 1 descendant associated to some scalar primary. So suppose that phi of x is a scalar primary of dimension delta. Okay. Then d mu phi of x is its level 1 descendant. Okay. And we want to know, how does this descendant transform? So we're going to start with a general conformal transformation. So So we'll take the general conformal transformation x mu going to x mu tilde equal to x mu plus psi mu, where psi mu is a formal killing vector. So when we solve the killing vector equation, this is just a mu plus omega mu nu x mu plus lambda x mu plus b mu x squared minus 2 b dot 2x mu b dot x. Again, the lambda parameterizes dilatations, the b parameterizes special conformal transformations, the omega parameterizes Lorentz transforms, and the a parameterizes path like this. So key to this next step is two things. Well, one main thing. So we're interested in the following. We want to know what is delta of d mu phi of x. Right. This will tell us how this guy, d mu phi of x, the descendant operator, transforms under this transformation. Okay. And key to this, to working this out, is the fact that I can commute the variation with the partial derivative. So this is just d mu of delta phi of x. So phi of x is a primary, and delta phi of x is how that primary transforms under conformal transformation. We know this from the last lecture. Okay, so we know what this is. This is just d mu of minus psi nu d nu phi minus delta omega phi. So this here is the conformal dimension of phi, and omega is just lambda minus 2b dot x. So basically the coefficient of x mu in this table. Okay. And you'll notice that there's no spin term in here. When I wrote down the transformation for delta phi, it had some term that has sigma mu nu in it, right? The sigma mu nu transforms any of the Lorentz indices that phi might carry. But this is a scalar, but it doesn't carry any Lorentz because there's no spin term. Okay, so that's what happens for a scalar. But now I can just take derivatives. Actually, I can just take derivatives, and this is just equal to minus psi nu d nu phi. All right, so this is the derivative of the descendant operator minus d mu phi nu d nu phi minus delta omega and it's delta times omega times d mu phi plus 2 delta B mu times phi, which comes from differentiating the omega. Okay, and this is it. This is our descendant transforms. There's something I'd like you to pay attention to here, which is an important point, namely that when we had the transformation of the primary operator, it involves the derivative of the primary operator. It's fine, I'm allowed to do that. And all other terms were proportional to phi. So they only involve the primary operator. So I could write down everything about the transformation of the primary operator in terms of the primary operator. Okay. Here, for the descendant operator, so that previous property was nice, and it meant that we could write the transformation of the primary operator as a tensor density. Okay. For a descendant operator, I have a derivative of the descendant operator, that's fine. I have the descendant operator, that's fine. I have another descendant operator, that's good. But here I have a primary operator. So the transformation of the descendant operator mixes descendants with primary, and it doesn't transform as nicely as primary. Right? So primary operators transform great. They only involve primary operators. Right? But this term here tells me that descendant operators do not transform as nicely as primaries. This is an important aspect of the optimization scheme that we're coming up with. Nevertheless, it would be nice to understand why I'm getting this term involving the primaries. To see where this term involving the primaries come from, let's see what a special effect on. Let's see what the effect of a special conformal transformation with some parameter B mu has on the primary. So to see where the last term comes from, let's consider the action of a special conformal transformation. So we generate a K nu parameterized by the B nu on the descendant. So I'm going to choose to write it with an I in front of it. Well, it's for convenience because I want to do something now, right? If I understand what the action on d mu phi is, understanding what the action on I d mu phi is brilliant. And by the arguments we made last time, only need to tell you what's going on at the origin, right? So let's work out what the commutator then is between b mu, k nu, and I d mu phi at naught. I know that I d mu phi of naught is just the action of the p mu operator, so I can replace this thing with a commutator. So that's v nu, k nu, with the commutator of p mu and phi at naught. And then I can use the Jacobi identity to shuffle around commutators. So this is just minus the commutator of p mu with the commutator of phi of naught and b nu k nu minus phi of naught, commutator of e nu k nu with p mu. Okay, and this comes from the Jacobi identity. I know that this here comes from the algebra, from the conformal algebra. So there's some commutator between K, mu, and P. There's this additional thing here, but I don't think right. This is defined by the conformal algebra. I also know that this guy is a primary, meaning that it's annihilated by this guy. So whether it's sitting on the left or the right, I can flip it around on the minus sign. Okay, and then I'll have the action of K nu on a primary, but that's a 0. So that's 0. And then I use the algebra, the conformal algebra, to rewrite this term as the factor of 2 minus 2i, phi naught, phi of naught, commutator with b mu d, d being the limitation operator, generator of limitations, plus m mu. B, and then there's one B on this. Okay, sorry. Okay, let me explain it and then I'll erase it. So don't write down. So this commutator here will pull out a d proportional to eta mu nu and an m mu nu. Right? This is from the conformal algebra again. The m mu nu acts on this guy. This guy is a scalar, so m mu nu acting on it is 0. Right? So this goes away. So the only term that remains from this commutator is this one. Okay. Again, because we're focusing on a scalar. So this is just 2 delta, because this acts on this, we pull out its conformal dimension. Conformal dimension is delta. 2 delta b mu phi of naught. And this is precisely this term here. Okay. So that's where this term arises from. It comes from the action of the special conformal transformation on the descendant operator. Okay. Okay. So good. So that tells us how descendants transform. And we're going to use all of this commutator technology in a little bit when we talk about correlation functions. But before we go there, I would like to elaborate a little bit on what unitarity has to do with norms. And in particular, I want to emphasize see how this works. Okay. All lines are designed so on the color. Yeah. Okay, well, let's see how it goes. Okay, so what does unitarity have to do with the norm of states? To illustrate this, I want to take a toy example. And the thing about this toy example is that it's neither realistic nor conformal, actually. But it'll illustrate the point that we want to make. Okay. When we say that a theory, a quantum theory, is unitary, what we mean is that its time evolution operator is a unitary operator. So a theory, by which I will always mean a quantum theory, is unitary if it is evolved by a unitary time evolution operator. So the time evolution operator u of t is e to the I times the Hamiltonian of the system times t. Okay. So for the theory to be unitary, I need this guy to be unitary, right? So unitarity means that u dagger of t, u of t is the identity, right? And this in turn means that the Hamiltonian must be Hermitian. Okay. So my theory is unitary if the Hamiltonian is Hermitian. There's subtleties about this that we can explore at another time. And one of them is that this necessarily implies, by theorems that you've learned from linear algebra, that the spectrum of the Hamiltonian is real. But it turns out that real spectrum, of course, the spectrum of the Hamiltonian is just the energy eigenstates of the system, right? The energy eigenstates can be real without this thing being necessarily Hermitian. So that's not the constraint that we want to impose. We want to impose a constraint that this guy is Hermitian, means that the theory is unitary. Okay. So let's consider a theory that's going to pose problems for this statement. And I'll explain why. So suppose I give you some theory with Lagrangian density L equal to a half d mu phi. That looks fairly normal. It's a kinetic term for a scalar, for a neutral scalar, minus a half m squared phi squared. Again, perfectly reasonable. It's a mass term for the scalar. Now I'll add to this some potential. This potential is kind of unusual from your perspective, but it's no big deal. It's just a linear term in phi. Okay, so this is a linear potential. But I'm going to impose that this field phi is anti-Hermitian. means that if I take the dagger of phi, it's actually minus phi instead of phi. All right. Let's first find the associated Hamiltonian and just do everything so that we're working in the Hamiltonian formalism. So what number are we on? 4. The Hamiltonian for this theory H, Hamiltonian density, is the momentum conjugate to phi times phi dot, so pi phi dot, minus the Lagrangian density, right? This pi I get by taking the derivative of the Lagrangian with respect to phi dot. So that can only come from here. And this is just phi dot. So this is phi dot squared minus the Lagrangian. So this is equal to a half pi squared plus a half gradient of phi dot gradient of phi plus m squared over 2 phi squared minus phi. Okay. So the question is this thing Hermitian? Right. So the first thing is that pi, the canonically conjugate momentum, is indeed anti-Hermitian as well. And that's because the anti-Hermitian property of phi itself, coupled with the canonical commutation relations between the phi's and the pi's, dictate that it must be anti-Hermitian. But another way to see that is just go ahead and calculate it, and it's phi dot. So if you take the conjugate of phi dot, you get minus phi dot, right? But I have two factors of this in here, right? So when I conjugate H, I'll have to conjugate pi twice, and that'll take care of the minus signs. Same here, same here. But this guy enters linearly as well. So the fact that phi is anti-Hermitian means that my Hamiltonian is no longer Hermitian, right? And this is a problem for unitarity. Is everybody with me? Okay, so I cooked up this theory, right? For the most part, it looks okay, but then there's this linear term which screws it all up. Okay, and my claim is that the Hamiltonian is not Hermitian, and by extension, the theory is not unitary. Okay. So how big a problem is this? Well, when you first learned about hermiticity, you learned it in the context of linear algebra. I gave you some matrix, and I said, you want to take the Hermitian conjugate of this matrix, you transpose it, and you complex conjugate all entries. All right. And then you came to no. And then you came to, I guess, second year differential equations, boundary value problems, maybe, where you were told that actually that's a lie. Well, it's not a lie, but it's kind of not the full truth. And that's because hermiticity is really a statement about the inner product that you're using. Okay, so in boundary value problems, or at the very least, third year mathematical physics, you should have learned that what is Hermitian or not is dependent on your inner product. Okay, so that definition of Hermitian came with the standard inner product in vector spaces, and basically you said that A, if I have some vector A, if I have some vector U and some vector V, then U inner product AV is the same as, if U inner product AV is the same as A dagger U inner product V, then A was equal to A dagger and you had a Hermitian matrix. So hermiticity is a function of the inner product that you're using to define it. Okay. So maybe all of this stuff is really just a function of the inner product. So let's see if we can pick an inner product. And again, I get to choose what inner product I want. Let's see if we can pick an inner product that cures the Hamiltonian of this problem. So can we pick an inner product that makes this Hamiltonian Hermitian with respect to that inner product? Okay, so I'm going to define a new inner product. Which I'll define with rounded brackets. So A inner product B will be defined as the standard inner product with angular brackets, but with a -1 to the number operator for particles created by the field phi. This is the number operator for particles created by phi. So this number operator could be even or odd depending on how many particles are in a particular state of the system, right? So why does this help in any way? Well, notice the following. Phi will change the action of phi, because this is the number operator for particles created by phi. The action of phi changes n by 1, right? So whatever the value of n is, acting then on that state with phi creates another particle, so it changes the value of n by 1. Well, since it changes the value of n by 1, the following identity is true. That -1 to the n phi is phi -1 to the n plus 1, or minus phi -1 to the n. In other words, the operator -1 to the n anticommutes with phi. So now let's calculate the matrix element of phi with respect to this new inner product. So A phi A. Okay, this is just phi some operator. I'm calculating the matrix element of this operator in this with respect to this new inner product. I don't really care what the state A is, right? The point is the following. When I convert this to angular brackets, the standard inner product, then this will come with a -1 to the n A which is minus a minus 1 to the n phi a. Oh, sorry, my bad. Yeah, there's an in-between step. What I want to calculate is not this guy. I want to calculate the dagger of this, because I want to show you that this inner product makes everything nicely conjugate, right? So there's a dagger there. And this dagger tells me that I should take kets and make them into bras. This guy is self-conjugate. No, sorry. This is a minus 1 to the n phi. And now I dagger this thing. So this is a phi dagger minus 1 to the n a. Phi dagger is minus phi. That minus sign comes from there. Minus 1 to the n. And now I flip these two around, which comes with a minus sign. So that's just a minus 1 to the n phi a, which is just phi a phi a, like that. So phi, the thing that really screwed up everything for our Hamiltonian up there, right, is Hermitian with respect to this inner product. Okay, so this means that phi is now Hermitian. And since that was the only obstruction, and you can go through and check that all of the other terms are perfectly fine with respect to the new unit product, our Hamiltonian is now Hermitian. Great. So we've managed to find an inner product that renders the Hamiltonian Hermitian. So what's the problem? Because there's a problem. Well, the problem is that any state with an odd number of particles, so if psi is a state containing an odd particle number, in other words, the number operator acting on psi is some 2n plus 1 psi, then the following is true. If I calculate in this inner product, the inner product of psi with itself, any odd particle number state, then this is psi minus 1 to the n psi. I can Taylor expand this guy and act order by order and then resum. So that's just minus 1 to the 2n plus 1 psi inner product psi. This is the standard inner product, right? And for the standard inner product, all states have positive norm, which means this is going to be minus psi inner product psi. So now I have negative norm states. So according to the previous inner product that we used, right, I had a Hermitian, sorry, according to the previous inner product I used, I had all positive norm states. All vectors in that vector space had positive lengths, right? But at the expense of the fact that I have a non-Hermitian Hamiltonian. So then I go around hunting for a Hamiltonian that makes, hunting around for an inner product that makes the Hamiltonian now Hermitian. I find it. But according to this inner product, I will necessarily have actually an infinite number of negative norm states, vectors with negative length. All right. So this is the problem with unitarity and norms of states and why we associate the norm of a state with unitarity. Okay. I think let's finish it. We don't have a lecture on Monday, right? It's public holiday. Okay. So next week, Wednesday, I will finish up the example on null states that I want to do, and then we'll talk about correlation functions.